it is. Let's see. So let's just take our time to wrap up. Last time we discussed quite a lot, some complicated features of electromagnetic waves. We were looking at waves propagating in metallic systems where the conductivity is not infinite. So there's a kind of coupling between the internal current density and the local field in there. Today, essentially, we're going to go back to a kind of perhaps simpler setup. We're going to consider perfect conductors, but shaped in a way that is rather intelligent. So what we imagine here is that we've got some form of hollow object. It can be of really any shape. Maybe it's a tube, maybe it's a kind of coaxial cable, maybe it's just a thin metal tube with no structure inside whatsoever. The point is that the surface of that thing is really a perfect conductor. So what occurs is that the perfect conductor, and if I imagine this thing just carrying on, right? So it's just like a full tube going through space. This perfect conductor here, you can visualize as a perfect boundary between two spaces, inside and outside, okay? And of course, the electromagnetic fields have to obey boundary conditions at this perfect conductor. But we can focus on the inside, because maybe our objective is going to be to propagate electromagnetic waves in a kind of directed fashion in such a contraption. Okay, so we're going to essentially look at solving Maxwell's equations inside such hollow constructions bounded by perfect conductors. And here by perfect conductor, I mean infinite conductivity, and therefore zero time scale for these things we were talking about last time, this kind of dissipation of the local free charge, etc. This occurs instantaneously. So really this this perfect conductor we will mathematically represent as boundary conditions. So what that means is that at the boundary so at the boundary, our electromagnetic fields have to obey some conditions, and the conditions are that the electric field parallel to the boundary has to vanish. Of course, if it doesn't vanish, then charge will reorganize itself such that it does vanish. Perfect conductor. The magnetic field perpendicular to the surface, that also has to be zero. Why? Because you remember, so as usual, everything comes out of Maxwell's equations. Div B is equal to 0. And then essentially I just do a Gaussian pillbox on the boundary. There's no discontinuity in the B, and B is 0 outside. Okay, therefore B perp is 0 outside. Is this echo coming from me or no? Okay, so these are the boundary conditions that we're going to use. So what will happen is that free currents will circulate on this surface. Okay, so as the electromagnetic fields are changing, the charge is going to be in motion on this surface in order to preserve these boundary conditions absolutely all the time, as the electromagnetic fields themselves dynamically move around. Okay, so what we're going to do is we're going to just give a kind of mathematical formulation for what kinds of waves can exist in there. So we're going to consider a relatively simple setup where I will use the same axes as before, so X, Y, and Z, and I'm going to imagine that I've got a certain shape. So although I don't need to specialize to that for now, let's imagine, I mean, we will do that later. Let's imagine that I have kind of a square or rectangular section contraption like this. And I've got waves propagating in the Z direction. But the electric and magnetic fields are going to be able to depend on the X and Y direction that I have here. So what I'm going to take is a kind of basic formulation for my fields here as a function of all coordinates in T. I'm going to say there's going to be polarization vector E0 that now will depend on X and Y. And it's going to propagate along Z. Okay, and the inside of this object is just pure vacuum. So again, it's filled with vacuum. Okay, and therefore the relationship between K and omega is that omega is equal to CK as per waves in vacuum. It's just now a bounded vacuum. Okay, and then the same thing for my magnetic field B. Yeah, so then it's a B0 again of XY, e to the I kz minus omega t. All right, so we can choose a polarization of this. You remember in free space, then there was really a kind of perpendicularity condition between the propagation and the polarization and the magnetic field. Inside a waveguide, funny enough, that doesn't have to be true. In fact, you know, it's not true. And you can find solutions that don't have this, this property. You got to generalize it a little bit. So general form for these electromagnetic waves inside waveguides in that particular kind of construction is that the I'll take this vector here E0 to be a sum of components in three directions. Yeah, so there's going to be EI and then I hat sum over I, where I here I mean X, Y, or Z. Okay, and then the same thing with B0. This is again just a sum of components in the X, Y, and Z direction, like this. Okay. Now we've got this form here, and we can do a direct substitution in Maxwell's equations. Okay, and you know you get a set of equations. So if I look at Faraday, this tells me that the curl of E is equal to minus dB dt. And that gives me the following three equations. So I'm going to take the X, Y, and Z components of that thing. The curl. So you know, let's take the maybe the first one is the Z component, easiest. So what do I get? I get equations like this. So partial EY with respect to X minus partial EX with respect to Y. So that's the Z component of the curl of E. That now has to be equal to the time derivative of the Z component of B. Okay, the time derivative gives me a minus I omega here in front, and then I've got another minus sign here, and then just pick out the Z component vector. So this is I omega B Z. Okay, and I'm writing straight the equation in terms of the coefficients here, because as we discussed last time, you know, these are independent functions. So therefore, the coefficients appearing on these orthogonal functions, they have to be equated. Okay, so that's directly the component form that you get. And then, of course, you get the other two equations. You get the dEz dy minus dEy dz. That's now equal to the IBX. And you also get the D. Actually, for the last one, here, you see when I compute the Y component, I got to take a Z derivative of E E in the X direction. And then the Z derivative does not act on this one because it's just depending on X and Y. And the Z derivative just pulls out an IK for me. Okay, so the last equation that I have here is just instead of having the ddz, I just pick up immediately an IK with the X and then dEZ dx. That has to be now the Y component, I omega B Y. And here, of course, there's an omega, right? Okay, so these are our three equations. Then the other condition that I get is from just Ampère-Maxwell. Okay, so Ampère-Maxwell in the so here I get similar things. So I've got the curl of B. I'm writing the equations now inside the conductor. So there's no J. The only J is on the surface. I'm now looking inside the thing. So here I really just have the curl of B is related to mu 0 epsilon 0 dE dt. So I'm just going to put that in there. So I get similar looking equations. I get that the dBy dx minus dBx dy, that's now minus I omega because I'm taking the time derivative of the x component. But there's the mu 0 epsilon 0, but mu 0 epsilon 0 is 1 over c squared. So I'm going to write that straight like this here. Okay, so that's the first of these other equations. And then the other ones they look like this. So dBz dy minus, again here I take the z derivative, but it brings out an ik by. This is now equal to minus I omega over c squared. And now the x bit, and the last equation is just ik bx minus dBz dx is equal to minus I omega over c squared E y. Okay, so these are essentially the solution. So the other two Maxwell equations are just like automatically, well, I guess we'll get back to just fulfilling those things just a bit later. So for now, we just make a start with Faraday and Ampère-Maxwell. Okay, so this is really just an equation now for the 6 coefficients, E, X, Y, Z, and B, X, Y, Z, given a certain K. Okay. So how do we solve that? Maybe let's just give some numbers to the equations. Let me use the same numbers here. 1, 2, 3, 4, 5, 6. Okay, so it's a bit of a mess. Yeah, question. Yes, absolutely. Yes, this is the Z. Thank you. So this one minus I, yeah, that was the Z direction. Thank you. Ah, good eyesight.
3 is 2 times in the X direction as well.
Because this is dEx dZ minus dZ dx, and here I take dZ. It simplifies because the only Z dependence is in the free wave that I have here, and just pulls out an IK for me. Okay, so that's how I get this thing. Okay, so these equations, we want to kind of smartly isolate what we need out of the. Now there are quite a few ways for doing this, but I'll just show you kind of what I think is the quickest way of writing one thing in terms of another. What we want to do ultimately is obtain a wave equation. Okay, you remember what we did with the electromagnetic waves in vacuum? We just decoupled the Maxwell equations between E and B by having, instead of 4 linear differential equations, we ended up with 2 quadratic equations in derivatives. Okay, so we're going to try to do the same thing here. So here we want to write fields, first of all, in terms of derivatives of fields. And then when we back substitute in the remaining equations, we're going to get second derivatives of fields. So a kind of wave equation like thing. Now, I think the simplest is to look at the equations for, let's see, so EX and BY. How am I going to do this? I want to do equation 3. And let me just find my way. I want to look at equation 5. Okay, and I'm going to rewrite equations 3 and 5 in the following way. You see, in terms of fields, in both 3 and 5, I have EX and BY. EX and BY. Okay, so I'm going to rewrite these equations, these two equations, in a little matrix form. Just want to show you this because maybe it's a trick that you can use. So in other walks of life. So what am I going to do? So 3 I can write as I with K times EX. And then minus omega by, like this, and this is now equal to dEz dx. The equation 5 I can rewrite as I times omega over c squared EX, and then minus K, parenthesis here, minus K by is equal to, and maybe I'll even like put a minus sign here for fun, just to put the positive sign here. So this is going to be equal to dBz dy. Okay, so you see the point is that I can rewrite this as a matrix relationship. I can just have a matrix K minus omega, and then minus omega over c squared and K, multiplying the vector now EX and BY. And this is going to have to be equal to, I've got an I on this side, I'll just multiply by minus I on both sides, minus I, the vector dEz dx and dBz dy. Okay, the reason why it's fun to do this is because, I mean, you know, matrix rules. Hopefully you can compute the inverse of a 2x2 matrix almost in your head. You've seen linear algebra, right? The inverse of a matrix is just, yeah, so if you have a matrix A, matrix minus 1 is 1 over that M with the cofactor. You're familiar with that term, cofactor? Yeah, the cofactor matrix transpose. Is everybody using that terminology? You know what I mean? So what you do, a cofactor, you got a matrix, and the cofactor ij is you take the matrix, you scrub row I and column J, and you compute the determinant of what's left. Have you seen that before? You've done linear algebra, no? So who has seen this before? Yeah. Okay, and who definitely has not seen this before? But okay, fine. Don't worry, it's not needed. I'm just kind of saying it as a useful tip for you when you do calculations on paper and whatnot, and you've got lots of linear relationships like that. Don't do like isolate the variable and then substitute and the whole thing and then go back substitute, back substitute, back substitute. It takes much longer. write it in a matrix form, and just invert the matrix straight like this. Okay, so but anyway, that's just like a friendly life tip that you can ignore. So so let's just see what we have here. So the determinant of our matrix M in our case is just k squared. K squared minus omega squared over c squared, and the inverse matrix is 1 over this thing, and then the transpose of the cofactor. So for example, if I want to do the this one here, I remove this and then take this one and then put the element. So I just get k, and then I get this one just omega, and then omega over c squared. Okay, so that's my inverse matrix. So essentially what I'm telling you is that we obtain equations for ex and by that look like this. So now I just have to multiply by the inverse matrix, and I've got this one here. So what this gives me is an equation for ex, which looks like this: I over put a minus sign here in the denominator, omega over c squared minus k squared, and then the parenthesis k with d e. We were doing e z dx, okay, plus omega db dbz dy, and the bx is equal to I over omega over c squared minus k squared, and then k dbz dy minus omega over c squared dez dx. Okay, that's just a way of doing this. Now, there's exactly the same kind of treatment you can do for the y components. You just need to choose the other two equations giving you this. So with the y components, you'll want to use yeah, 6 and 2, yes. And this is going to give you equations for EY and BY, which look a little bit similar. I'll just write it down. So this is now K D E Z dy minus omega d bz dx. And by is I over minus k squared, k dbz dx plus omega over c squared, and then dez dy. Okay, like boring substitution, really kind of slightly tedious to get right. However, now what we can do is we can put this back. So these equations here give us a relationship between, ex, ey, and these derivatives here. So let's look at these two equations for ex and ey. We also have Gauss's law, okay? So Gauss's law is obeyed with zero source in the waveguide, right? Because once again, I'm writing the equations for the electromagnetic fields inside the waveguide, where there's no matter, there's nothing there to carry anything. So there's no density, there's no current. And this tells me that dx of ex plus dy of ey plus dz of ez is equal to 0. And actually, if I substitute the this whole thing in here and compute explicitly the dz ez, you know, from this here, giving me another factor of ik, what this one gives me is directly a wave equation. Okay, the cross terms fall out. So for example, the dbz dx dy, that's coming here, coming from, you know, I do dx of this, I do here dx dy of bz, but then I'd have to do dy of this one, giving me minus the same thing. So this falls away. And then here I keep a second derivative of ez with respect to x, a second derivative of ez with respect to y. Okay, and then with the other one, so essentially what I get is an equation telling me that the second derivative with respect to x plus the second derivative with respect to y plus the combination omega over c squared, yeah, because I just can remultiply it by that thing, minus some k squared here. All of that applied to ez, that is 0, okay? And same for bz. Okay, so that is the wave equation that we were seeking. Okay, I'll make sure I don't use too much time on all of this. Yeah, I'm going way too slow. So this is the wave equation that you obtain in generic form inside such a waveguide. Okay, and the only thing we've assumed here is that there's propagation in the z direction, and there are boundaries somewhere in the x and y directions. Okay. So any kind of shape that is translationally invariant in z, even if it's irregular in the x and y direction, if it's translationally invariant in z, it will carry solutions, it will carry electromagnetic waves fulfilling this equation, but now with the proper boundary conditions for any particular case.